How is an object's acceleration related to the net force acting on the object? This is the question that students will explore in Investigation 5A, Newton's second law. In this investigation, students build on their understanding of motion in one dimension by exploring how an object's motion changes when a non-zero net force is applied. By now, students should be comfortable with one-dimensional motion graphs and have a clear understanding of what a net force is. For this investigation, each student group will need a smart cart with the hook attachment, two 250-gram cart masses, a dynamics track with feet, a super pulley with clamp, some thread, and a mass hanger with 5 washers. Students should assemble their equipment like this, with the end of the track hanging off the edge of their lab table, 2 cart masses in the top of the smart cart, and 1 washer on the mass hanger. In this setup, the hanging mass applies a force through the thread to the front of the cart. When students release the cart, the force from the thread will cause the cart's motion to change. Students will explore how the applied net force affects the motion of the cart by measuring force and velocity using the cart's built-in sensors. A couple of important things students should check before beginning their experiment. 1, make sure the track is level. Students can test this by placing the cart in the center of the track. If it rolls, it's not level. Adjust the track feet to level it. 2nd, make sure the thread is also level. Students can adjust the height of the pulley to make sure that the thread is level. Once the equipment is assembled, each group will open the experiment file 5A Newton's second law in SPARKvue. When the file is open, students can connect their smart cart using Bluetooth. Groups are now ready to begin recording data. Before recording data, students should zero the force sensor on the smart cart while nothing is touching the hook. Click the 0 button in SPARKvue to do this. To collect data, students should follow these steps. First, draw the cart back until the mass hanger is just below the pulley. The mass hanger should not be swinging. Next, start recording data and then release the cart. Catch the cart before the cart rolls into the pulley and stop recording data. Velocity data should be smooth and sloped upward while the cart was rolling freely, and the force data will look more like a flat line. In my graph, the velocity data is blue and the force data is orange. The force data may be noisy, but that's okay. Students will be averaging that data. Students repeat the same procedure 4 more times for a total of 5 trials, adding 1 more washer to the mass hanger in each trial. Adding an additional washer in each trial systematically increases the applied force on the cart. For each trial, students find the cart's acceleration and the average net force on the cart while it was rolling freely down the track. To find the average net force on the cart, students can highlight the data in their graph corresponding to when the cart was rolling freely down the track. Once the data is highlighted, you can activate the statistics tool that gives you the mean of that data. You see here from my data, I have an average net force of 0.8748 newtons. When students determine this value, they then record that into table 1 in their student handout. And you'll see here in my table, I have runs 1 through 4 already populated in the table. I'm going to go ahead and add run number 5, 0.8748 or 875 newtons. Okay, and to determine the acceleration of the cart, students can highlight their velocity data during the same time which the cart was rolling freely down the track, and then activate a linear fit. The slope of this linear fit is equal to the acceleration of the cart. And in this case, my acceleration is 1.150 meters per second squared. Once table 1 is full, students go to the second page of the experiment file and enter the data from table 1 into the table on this page. You'll see here I have runs 1 through 4 already entered. Let me enter run number 5. I had a net force of 0.875 newtons. and an acceleration of 1.150 meters per second squared. And you'll see when data is entered into the table, it automatically appears in the graph next to it. The questions in this investigation examine how the cart's acceleration changed as the net force on the cart changed. And they also make connections between the shape of the net force versus acceleration graph and the mathematical model for Newton's second law. Students should sketch their net force versus acceleration graphs, keeping in mind the general scale of both the vertical and horizontal axes. From their graphs, students should identify that the acceleration of the cart increased as the net force on the cart increased, and that the shape of the graph is a straight line or linear. For question D, students should use the linear fit tool in SPARKvue to determine the slope of their force versus acceleration graph and discover that the slope is equal to the mass of the cart plus the cart masses. Groups having trouble identifying this should recognize that the units for slope are newtons over meters per second squared, which is equal to kilograms, the units for mass. Finally, question E has students connect the mathematical model for Newton's second law to their data. Students should identify that the F equals ma model represents a linear graph between force and acceleration, similar to their data, with the slope equal to the mass of the object, which students identified in question D. Historically, Newton's second law investigations involved indirect measurements of net force, which often caused confusion with students. The use of the smart cart in this investigation eliminates the potential confusion because it directly measures the applied net force, a great conceptual benefit to students.